crystals, the refractive index variation is very small at this particular wavelength. The variation is always very less for isotropic crystal, whereas in the case of an isotropic crystal, the variation of refractive index is little large compared to that of isotropic crystals. Okay. Now, another important property, that is birefringence of an isotropic crystal. It is actually the optical property of a material. So here, look at this diagram. Here, an unpolarized light falls on the surface of the crystal. Okay. Now, at the surface of the crystal, this beam splits into two different beams with orthogonal polarization and travels in different directions with a different velocity. Okay. Now, you can see one unaltered line and another one is another line you can see. So, this line, unaltered line, is known as ordinary wave or O-ray, and the other line is the extraordinary ray. So this property is known as, this phenomenon is known as birefringence. When a beam of unpolarized light falls on an isotropic crystal such as calcite, quartz, or KDP, it split into two beams at the crystal surface. These two beams propagate in two different directions with different velocities, and they have mutually orthogonal planes of polarization. This phenomenon is known as birefringence, and such crystals are known as birefringent crystals. Okay, here you can see two crystals. One is isotropic and the other is anisotropic, and here some lines are there. So when you view this line with isotropic crystal, you can see only one line, but using an anisotropic crystal, if you view this line, you can see two, one same line, unaltered line, and the other is a new line. So this unaltered line is due to the ordinary wave, and the new line is due to the extraordinary wave. And this is because of the birefringent nature of the anisotropic crystal. So such crystals exhibit double refraction. Because of that, you are seeing two lines. Okay. So in general, we can say that birefringence produces two different rays. One is ordinary ray and the other is extraordinary ray. This ordinary ray always obeys Snell's law of diffraction, whereas extraordinary ray does not obey Snell's law of refraction. Okay. Now, another property is a ordinary ray always propagate inside the isotropic crystal itself can be classified into two groups, that is positive crystal and negative crystal. In the case of positive crystal, example quartz, the ordinary ray travels faster than extraordinary ray. Therefore, the refractive index for the ordinary ray is less than that of extraordinary ray because refractive index and velocity are inversely proportional. Okay. Now, ordinary ray means it obeys Snell's law and it travels with the same velocity in different directions. So, such waves can be represented using spherical wavefront. And extraordinary ray have different velocities in different directions. So, we can express it with elliptical wavefront. Okay. So, in the case of positive crystal, ordinary ray travels faster. So, the spherical wavefront moves faster than that of elliptical wavefront. So, therefore, this is the structure for that. In the negative crystal, example calcite, the velocity of ordinary ray is less than that of extraordinary ray, and hence the refractive index is more for ordinary ray. Okay, so VE is larger than that of VO. Therefore, elliptical wavefront exceeds the spherical wavefront. Okay. And in this table, I have listed some principal indices for various crystals. Okay. So here isotropic crystals are also there. Anisotropic crystals are also there. So for isotropic crystals, we know that there is no birefringence. Therefore, it possesses only a single refractive index throughout the crystal. So example for that is glass, diamond, fluorite, etc. But anisotropic crystals, again classified into uniaxial and biaxial crystal. Uniaxial crystal means they have only one optic axis, and biaxial crystal means they have two optic axes. Okay, and for uniaxial crystal, we can see there are two refractive indices. One is for ordinary ray and the other is for extraordinary ray. And again, uniaxial crystals are divided into two, positive and negative. And for positive crystal, we know that ordinary ray travels faster than that of extraordinary ray. Therefore, refractive index is less than extraordinary ray. Okay, in the negative crystal, it is reverse. Okay, and in the case of biaxial crystal, you know that there are two optic axes. So one more additional refractive index will be there for such crystals. So in addition to two, one more is there, that is for ordinary ray. Okay. Now, finally, in the introduction part, retardation plate. These are very important. Retardation plates are optically transparent material that works on the principle of birefringence. That is, at the crystal surface, it splits into two different beams. Incident light split into two different beams, and this retardation plate retards the phase of one of the component relative to the other, and at the output, they recombine and form a single beam with new polarization. Okay, here two diagrams are shown. In the first diagram, you can see that this is the optic axis, and optic axis is parallel to the surface of the crystal. And in the second diagram, optic axis is this. It is perpendicular to the crystal surface. So here, the input wave is incident on this linearly polarized light is incident on the surface, normally to the optic axis. Then it won't split into two, because this is the property of these two cases. When light is incident along with the optic axis, it won't split into two. Again, when the light is incident normal to the optic axis, again it will not split into two, but it will travel in the same direction but with a different velocity. So this is for the first case, but here the input light is incident parallel to the optic axis, then it will not split into two waves. It will travel with the same velocity. Okay, you can see here it is traveling with the same velocity, but here it is different velocity. So this is retardation plate is doing. There are two types of retardation plates or wave plates. That is half wave plate. The other one is quarter wave plate. Okay, half wave plate is actually shift the polarization direction of linearly polarized light by producing a phase difference of pi and a corresponding path difference of lambda by 2 between E ray and O ray. Whereas quarter wave plate converts linearly polarized light into circularly or elliptically polarized light, and vice versa by producing a phase difference of pi by 2 and a corresponding path difference of lambda by 4. The path difference lambda by 4 ആയതുകൊണ്ടാണ് ഇതിനെ quarter wave plate എന്ന് വിളിക്കുന്നത്. ഇവിടെ path difference lambda by 2 ആയതുകൊണ്ടാണ് ഇതിനെ half wave plate എന്ന് വിളിക്കുന്നത്. So actually half wave plate shift the polarization direction, whereas quarter wave plate convert a polarization into a different state of polarization. And the phase difference between the O ray and E ray can be calculated like this. 2 pi by lambda into path difference is the equation for phase difference. Path difference can be estimated by taking the difference in the refractive index of O ray and E ray into the thickness of the medium. So by adjusting the thickness, you can create either half wave plate or quarter wave plate depending on the phase difference. Okay, here you can see the input and output of half wave plate and quarter wave plate. Here the input is linearly polarized light, and for an arbitrary incident angle, it will produce in the output half wave plate produce again linearly polarized light but with different orientation. But in the case of quarter wave plate, if the incident angle is between 0 and 45, this linearly polarized light is converted into an elliptically polarized light. If the incident angle is 45 degree, input incident angle is 45 degree, then you will get circularly polarized light at the output. Okay, this is what retardation plates do. Okay, now we move on to our topics, that is modulation, electro-optic effect, and electro-optic modulators. And these are part of this, but I'm not going to discuss more about this. Just I will touch upon these things because of time lag. Okay. Now, first, modulation of light. What is modulation? Modulation is actually the property or the process of varying the optical properties of a carrier wave with a modulating signal that contain information to be transmitted. Normally, telecommunication, in electronics and telecommunication, modulation is to send the signal from one place to the other. So, for doing this, we are encoding the data or information in the carrier wave and transmit it, and at the receiver end, it will be decoded. Okay, so here you can see three different diagrams. So one is for amplitude. There are three types of modulation. One is amplitude modulation, or in other words, we can say intensity modulation, because amplitude and intensity are related. And the second one is frequency modulation, and third one is phase modulation. So for these three modulations are pictorially represented here. So this is our message signal data, and this is our carrier signal. When you encode this data information in the carrier signal, you will get either amplitude modulated or frequency modulated or phase modulated signals, depending on the procedure. Okay, so here you can see the variation in amplitude. Here you can see the frequency variation with the time, and here you can see the phase variation. Okay. Okay, modulators has many applications in, modulators have many applications in various areas. So it can be used in optical communication systems because light can be modulated at very high frequencies from megahertz to gigahertz. So it can be used for optical communication, and it can also be used widely in signal processing and have many applications in integrated optics such as optical switches, directional coupler, etc. Okay, now methods for modulation. So modulation can be achieved in two different ways. One is internal modulation, or the other one is external modulation. Internal modulation are also known as direct modulation. External modulation is also known as indirect modulation. In the internal modulation or direct modulation, a circuit is actually designed to modulate the current is injected into the device. That's why it is called internal modulation. Whereas in external modulation, the medium that passes the optical signal is under the control of an external circuit. Okay, there are many advantages and disadvantages for these two methods. First, there is less advantage for indirect modulation. It is very simple process. That's the only advantage of indirect modulation, but many disadvantages are there. The first one is modulation can be achieved only for a frequency less than or equal to 40 gigahertz. But in the case, second disadvantage is the emission frequency change with the input current. That is second disadvantage. And third disadvantage is only amplitude modulation is possible with ease. These three are the disadvantage for internal modulation or direct modulation. In the case of external modulation, they have many advantages and only one disadvantage. So one of the advantages is high speed, and its speed is controlled by the modulator property. That is one of the advantage of external modulation. And a second advantage is emission frequency is independent of input current. It is unaffected. And a third advantage is both amplitude modulation and phase modulation are possible with ease. But in the case of direct modulation, only amplitude modulation can be easily done. Okay, here amplitude and phase modulation is very easy. And one of the disadvantage of this external modulation is the modulator size is large compared with the scale of microelectronic device, and hence cannot be part of the same integrated circuit. That is the only disadvantage of this external modulator. Okay, now in this talk and in your syllabus, we are discussing only about external modulators. We are not even discussing about internal modulators. So the external modulator design, there are three different designs for external modulator. One is based on electro-optic effect, and the second one is based on magneto-optic effect, and the third one is based on acousto-optic effect. If the design is based on electro-optic effect, then such modulators are known as electro-optic modulators, in which the applied electric field is actually changing the optical property of the medium. Okay. In the case of magneto-optic modulator, the applied magnetic field is responsible for the changes in the optical property of the medium. And here in acousto-optic modulator, the mechanical strain produced by the passage of acoustic wave is responsible for the change in the optical property of the medium. Okay, so this acousto-optic effect, you already know about this. I think in your lab you are doing ultrasonic experiment. So in that, acoustic waves, mechanical strain is produced by the piezoelectric crystals and form an artificial grating inside the medium. And when light is incident on this artificial grating, it gets diffracted. So you are viewing that diffracted images. If the thickness of this artificial grating is large, then you will get Bragg diffraction. You can see only one diffracted mode, one diffraction image. But if the thickness is less for this artificial grating, you may get multiple diffraction orders. So such diffraction are known as Raman-Nath diffraction. If you are getting only a single diffraction pattern, then that is known as Bragg diffraction. Okay, so based on that, acousto-optic modulators are of two types: Raman-Nath modulator, and the other one is Bragg modulator. And in the case of magneto-optic modulator. Faraday rotator is an example. With applied magnetic field, the rotation axis will be different for such modulator. And we are discussing here only about electro-optic modulator based on the configuration and modes of operation. They are classified into two. One is longitudinal electro-optic modulator. The other one is transverse electro-optic modulator. So we are discussing more about this part. Okay. We have seen three different modulators now, but of the three, electro-optic modulators have many advantages. So the advantages because of its fastness. So these type electro-optic modulators are most common in high-speed communications, and the technology used in such devices is compatible with that of semiconductor devices. So electro-optic modulators are most commonly used. Okay, now we can define what is electro-optic effect. So this is the definition. By the application of an external electric field across a crystal, the refractive index may change in the medium and may induce birefringence in an isotropic medium, and it may alter the existing birefringence property of an anisotropic medium. So this effect is known as electro-optic effect. So I will tell once more. When we apply an external electric field across a crystal, it may change the refractive index of the medium. It may induce birefringence in an isotropic medium. We have already seen that in isotropic medium, there is no birefringence. But when an isotropic medium is placed in the presence of an external electric field, it may induce birefringence. Okay. Similarly, already existing birefringence property can be altered in the presence of external electric field. So this effect is known as electro-optic effect. Okay. Now let us see how the electric field is affecting a lattice. Okay. Now here is a lattice. In the absence of electric field, here is the same lattice in the presence of electric field. Here you can see that the lattice is very symmetric when we view from orthogonal directions because there is no field. So the lattice is constant. It is very symmetric. But the same lattice in the presence of electric field will look like this. So electric field is applied along this direction. We know that when an atom is placed in an electric field, its positive and negative centers will be shift apart and produce a dipole. Okay. Similarly, the positive centers of the atom in this lattice shift along the direction of electric field so that the lattice gets distorted. And this distortion in the lattice induces anisotropy in the medium. Okay, this is the reason why electro-optic effect is happening. Okay, here is the index diagram. Again, in the absence of electric field, and this is in the presence of electric field. So in the absence of electric field, for an isotropic medium, this is the index diagram. Index diagram means it is the diagram. Okay. It is the diagram that shows the orientation and magnitude of refractive indices in the crystal. Okay. So here in the isotropic crystal, it is spherical in structure. So we know that for isotropic crystal, there is no birefringence. The light travels with the same velocity in all the direction. Therefore, the refractive index for X is equal to the Y direction and equal to refractive index of Z direction, which is equal to the NO, that is for the ordinary ray. So the equation for this index index diagram is this, that is that of the sphere x square plus y square plus z square equal to n0 square is the equation for this index diagram. Now, the same lattice or same material is placed in an electric field. So we know that in the presence of electric field, this lattice will get distorted. So you get a new index ellipsoid diagram. This is an ellipsoid. It is elongated along the direction of electric field. Hence, the refractive indices for three different axes is different. So this is an ellipsoid and the corresponding ellipsoid equation is this. Okay. Remember this equation. We are using this after a while. Okay. Here we can derive the variation of refractive index under the influence of electric field. Okay. Now we know that the variation of refractive index is very small with electric field. Okay. Therefore, we can apply Taylor series expansion. So n of e, it can be written as n of 0 plus the first derivative of n with respect to e into e plus half second derivative of n with respect to e into e square, etc. Since the variation is very small in refractive index, we can truncate the series here. Okay. So n of e can be written as n of 0. N of 0 means the refractive index in the absence of the field, plus this can be taken as a constant because the derivative at e equal to 0. This is a constant. So a1 e plus 1 by 2, another constant a2 into e square, etc. Okay, no etc. because we are truncating here. Okay, now find out the difference in the refractive index. So delta n equal to n of e minus n of 0. This is the induced by refringence because of the presence of electric field delta n. That is n of e minus n of 0, which is equal to a1 e plus half a2 e square. So here you can see that there are two terms. One is the change is linearly related to this term and is quadratically related to the second term. So based on this, electro-optic effect can be classified into two. One is focal effect and the other is Kerr effect. In focal effect, the change in refractive index is directly proportional to the electric field. Hence, it is known as linear electro-optic effect. Okay, because the change in refractive index or induced by refringence is linearly related to the applied electric field. Okay, this effect is known as focal effect. Okay, in the case of Kerr effect, this change in refractive index is proportional to the square of the electric field, applied electric field. So this effect is also known as quadratic electro-optic effect. Okay, we are concentrating here in the Focal's effect. Okay, not more on the Kerr effect. Okay, now we are introducing a parameter eta, that is impermeability tensor, which can be written as 1 by n square for the medium. Now the change in eta or change in impermeability tensor can be written as delta of 1 by n square. Now just to differentiate this, you will get this. So this is the differential of this is minus 2 by n cube into delta n. And we already know delta n is a1 e plus half a2 e square from Taylor series expansion. Just substitute this here, you will get this equation minus 2 by n cube a1 e plus 1 by 2 a2 e square. Now the just open the bracket. Now you will get this equation. Okay, here this can be taken as a constant r, and the second part, this part can be taken as a constant p. This r is related to the linear effect, so it is known as Focal's coefficient, and p is related to the quadratic term, So it is known as Kerr coefficient. Okay. Now the delta eta, the change in impermeability equation becomes R into E plus P into E square. Okay. And from here, here you can see that delta eta equal to minus 2 by n cube delta n. So from this equation, you can estimate delta n as minus n cube by 2 delta eta, minus n cube by 2 delta eta. Substitute the value of delta eta here, you will get the equation for induced birefringence delta n, which is equal to minus n cube by 2 r dot e minus n cube by 2 p dot e square is the equation for induced birefringence. Okay. Now consider two cases. Sorry, two cases. Here we are considering certain materials like a KDP. Sorry. So in such materials, the P term is negligible. So the second term is negligible. So we can avoid this term. That means only the first term exists in this equation. It shows that KDP exhibit only Focal's effect, not Kerr effect, because this part is negligible. And here some other materials which show centrosymmetric structure. In such cases, R term is 0 or R term is negligible. That means this term will be 0. So only this term exists. That means this materials with centrosymmetric structure shows only Kerr effect, not Focal effect. So this KDP crystal shows only Focal effect. Now we can just find out what is the change in refractive index or induced birefringence in Focal's effect. Okay, the typical value of Focal's coefficient ranges from 10 raised to minus 12 to 10 raised to minus 10 meter per volt. Now, and for a fixed value of electric field 10 raised to 6 volt per meter, now we can estimate delta n as this is the equation. So you will get a range that is 10 raised to minus 6 to 10 raised to minus 4. So which is very small. The Focal effect, the induced birefringence, the change in refractive index in the variation matrana. Now, in the case of Kerr effect, the Kerr coefficient P changes from 10 raised to minus 18 to 10 raised to minus 14. And for the same fixed electric field, the change in the refractive index is of the order of 10 raised to minus 6 to 10 raised to minus 2, which is quite larger than this previous case. Okay. So anyway, the variation of refractive index is very small in both the cases. Okay. Now, in fiber optic communication, the Focal's effect or linear electro-optic effect is most commonly used to modulate the signal in accordance with the applied electric field. So, as I told you earlier, linear electro-optic modulator has two different modes of operation. One is longitudinal mode of operation. The other is transverse mode of operation. The longitudinal mode of Focal's modulator can do phase modulation and amplitude modulation, whereas the transverse mode is mainly used for phase modulation. Okay. Now, here is the schematic diagram for linear electro-optic modulators or Focal's modulator. So here, longitudinal and transverse configuration we are considering. What is the difference between these two? Here in the case of longitudinal electro-optic modulator, the transmission axis or the propagation axis is along the Z direction, and electric field is also applied along the Z direction. So here you can see that electric field or voltage is applied across the length of the crystal. Here in transverse mode, the electric field is applied across the width of the crystal. and propagation direction is along the Z direction. In both modes, the propagation direction is Z direction, whereas electric field is applied parallel to the Z direction in longitudinal case, whereas it is perpendicular in transverse mode. Okay. Now, here we are using the crystal as KDP or ADP or KD star. That is class 4 to materials are crystal use medium electro-optic medium use. So, these crystals in the absence of field, it is uniaxial in nature, and in the presence of field, it will become biaxial. Okay, now class 4-2 means it has a fourfold symmetry axis. Here it is Z. Z is the fourfold symmetry axis, and have twofold symmetry axes. X and Y are twofold symmetry axis. What is fourfold axis or n-fold axis of symmetry? So we have already studied in mathematical physics that. So any rotation by 2 pi by n leaves system invariant, then we call it as n-fold symmetry axis. Okay, so here Z is fourfold symmetry axis and X and Y are twofold symmetry axis for this crystal. Okay, now here is the structure of longitudinal or Focal's electro-optic modulator. Okay. So here an incident beam polarized along this direction, that is X prime direction. Polarization direction ആണ് ഒരു polarizer ഉണ്ട് ഇവിടെ. ആ polarizer ഈ direction X prime directionലാണ് incident light polarize ചെയ്യുന്നത്. So that is incident on this crystal, which is KDP, and here electric field is applied parallel to Z direction, and this is the emergent beam. Okay. So Z is propagation direction. Input polarization is along X prime, which is making an angle 45 degree with the X direction. And X prime is actually the induced principal axis in presence of the field, X prime. Okay. And in the absence of the field, suppose if we apply a voltage 0 here, then there is no electric field. The index ellipsoid can be written like this. As we seen earlier, x square by n0 square plus y square by n0 square plus z square by ne square equal to 1. This is the index ellipsoid equation in the absence of the field. And here there is no birefringence. Okay, means birefringence is there because we are using KDP crystal, which is uniaxial. Okay, and when the field is 0, Nx and Ny are same, the refractive index, which is equal to NO, that is for ordinary ray, and Nz equal to Ne, this is for extraordinary ray. When we induce or when we apply an external electric field, this index ellipsoid will be modified to this form because these are the principal axis. In the absence of X, Y, and Z are the principal axis in the absence of electric field. Now, in the presence of electric field, X prime, Y prime, and Z prime or Z prime is the new induced axis. Okay. Now, the corresponding refractive index N0 can be. So, this is already a uniaxial crystal. KDP is a uniaxial crystal. When in the presence of electric field, it will become a biaxial crystal. Okay. For uniaxial crystal, you will get only 2 refractive indices for the media. But in the case of biaxial crystal, you will get a 3 refractive index because an induced birefringence or the birefringence is altered in the presence of electric field here. So the new changes is Nx prime and Ny prime. So the change in the refractive index is this N0 plus NO plus N0 NO cube by 2 R63EZ, which is related to linear electro-optic effect, and N0 minus N0 cube by 2. These are the new refractive indices for the medium. Now, let us go back to the old equation. This is the index ellipsoid equation. Here, these are the new changes, okay, because of the presence of electric field. So, since KDP crystal exhibit linear electro-optic effect, we can write the change in refractive index, or this is actually impermeability factor, delta of 1 by n square. We know that it is R into E for linear electro-optic or focal effect. Okay, and so we can write this parameter as R41 EX. R41 means this is focal coefficient, non-zero focal coefficient, R41, and this is for y direction. So here ZX, so electric field is in the y direction, and here delta 1 by n square XY, and electric field is in the z direction. Okay, so these are the changes. Now apply these in this equation, you will get this equation. Okay, x1 x square plus y square by n0 square plus z square by ne square, plus the changes is in the crossover terms. Well, this is the new index ellipsoid equation. Okay, and here in longitudinal electro-optic modulator, electric field is applied along the z direction. Therefore, EZ component remains, and all other thing EX and EY is 0 here. So this equation can be rewritten as this, eliminating these two terms. Okay, this is the new equation for our medium. Okay, now closely watch this equation. You can see that there is no crossover term involving Z in this equation. The only crossover term is this X and Y. There is no Z present. That means Z and Z prime is same. That means there is no change in the Z direction because of the application of electric field. And we can also see that there is a symmetry between X and Y. So this shows that the X and Y axis and the new induced axis X prime and Y prime, they are related by an angle 45 degree. Otherwise, you cannot see any symmetry. Okay, so the angle between X and X prime or Y and Y prime is 45 degree. So using this information, we can find out the induced axis X prime using coordinate transformation. X prime equal to X cos 45 plus Y sin 45. Y prime is minus X sin 45 plus Y cos 45. And which is equal to X plus Y by root 2 minus X plus Y by root 2. And there is no change for the Z axis because here you cannot see any crossover term in Z. Okay. From these equations, find out the inverse equation, inverse transformation equations, that is X equal to X prime minus Y prime by root 2, Y equal to X prime plus Y prime by root 2, and Z equal to Z prime. Apply these equations, these three equations in equation number 1 and simplify, you will get this equation. Okay, now like terms and coefficient കണ്ടുപിടിക്കുക. X prime square and Y prime square Z. There is no other term for Z. And like terms number club here, find out the coefficient. And now this equation can be rewritten like this. That this is 1 by nx square, X prime square. So X prime square by nx square plus Y prime square by ny prime square plus Z square by n square equal to 1. This is the new ellipsoid equation. Now, from this, that is 1 by nx square equal to this. So you can find out what is nx prime square or nx prime. And from this, you can find out ny prime. Nx prime is actually this raised to minus 1 by 2. Okay, this raised to minus 1. Expand this equation, and you can approximate this with the first term. Now this equation becomes N0 minus N0 cube by 2 R63 EZ. This is the change in refractive index along x prime direction, and along y prime direction there is same terms, but there is only a small change in the direction, means sign. Okay, so these are the new refractive indices for the medium now because of the presence of electric field. Now we can find out induced birefringence delta n. So the major change is in this two directions. So delta n x prime y prime is the induced birefringence, which is equal to n x prime minus n y prime. Just subtract these two together, you will get N0 cube R63 EZ, where EZ is V by L. The voltage is applied across the length L. Therefore, E equal to V by L. So now we can find out induced phase shift. Induced phase shift is 2 pi by lambda into path difference. Path difference can be found out using this equation delta n into L. This is the path difference. So delta n, you can substitute this here, and you can see that this L and this L cancel each other, and the induced phase shift is 2 pi by lambda N0 cube R63 V. This is the induced phase shift for linear electro-optic modulator. From this equation, it is clear that the change in phase shift or retardation is directly proportional to the applied voltage and is independent of the length of the medium. Okay, this is very important. The induced phase shift is proportional to the applied voltage and is independent of the medium in the case of linear electro-optic modulator. Okay, now we can use this medium as a half wave plate. Okay, so half wave plate we know is pi between the components of electric field, orthogonal components of electric field. So in the case of KDP, when it can be used as a half wave plate, just apply a voltage corresponding to a phase difference of pi. Okay, so so you can substitute directly here delta phi. This is induced phase difference, which is equal to 2 pi by lambda thus. And when this is equal to pi, you will get the half voltage for this linear electro-optic modulator. Okay, so from this you can find out what is the voltage you have to apply in order to get a phase difference of pi. That is V pi. This is known as half voltage. V pi is lambda by 2 N0 cube R63. E pi cancel the. So the reminder this. Now, for a KDP crystal with a wavelength 0.6, we can just calculate what is the value of this half voltage. Okay, the half voltage in the voltage required to induce a phase difference of pi between the orthogonal components of electric field. Okay, so ഇവിടെ നമുക്കൊന്ന് ഈ wavelength ഇട്ടിട്ട് ഈ half voltage ഒന്ന് കണ്ടുപിടിച്ച് നോക്കാം. You will get, so you cannot, okay, you will get 8.3 kilovolt ആണ് നമുക്ക് ഇവിടെ കിട്ടുന്ന induced voltage. Okay, you have to remember this value because we will discuss about this later. Okay, so for linear electro-optic modulator, the half voltage is 8.3 kilowatt, which is quite high. Okay, now we are going to use linear electro modulator as a phase modulator. As I told you earlier, linear electro-optic modulator or 𝐒𝐜 modulator is used. Linear longitudinal setup can be used for phase modulation and amplitude modulation, whereas transverse mode is mainly used for phase modulation. Okay, now longitudinal setup phase modulator use So it is very simple. Just apply a variable voltage here. Earlier voltage apply here we are applying a variable voltage V0 sin omega t. Okay, now here we are assuming that x prime is the direction of incident polarized light. X prime is the direction of incident polarized light, which is making an angle 45 with the x direction. Okay, so this is the linear polarization direction. Now, when this light is incident, again birefringence will take place and all other things will happen. Now, what is the emerging light from this side in the output? We want to know what is Ex prime at ZL. So, which is equal to Ex prime 0. 0 means at 0. E side electric field in the component into cos omega t minus kz. Z is actually the path difference. So nx prime into L is Z. Okay. So now substitute the value of nx prime here. So nx prime we already estimated in the previous slide. So nx prime equal to n0 plus n0 cube by 2 r60. Just substitute that value here and open the bracket, you will get this equation. Okay, so the second part is actually a constant factor K0, N0 and L. This is a fixed phase part. It is not depending on the applied voltage. And the third part is actually depending on the applied voltage, which is variable now. Okay, so Ez actually V by L, and L will cancel each other. So this is V. So equation will be like that. The first and second part is constant, and the third part, modulated part, phase modulated part. Okay. Now we can assume this as a constant P. P is written here. That is K0 N0 cube by 2 R63 V0. This is known as, this P is known as the phase modulation index. Phase modulation index. So in the there is a sinusoidal variation with the peak value of P, and this P, the phase modulation index, will be maximum when sin omega t is 1. Okay, so now it modulated the phase. Okay, now earlier we said that the input light is polarized along prime direction. Let us see what will happen if it is polarized in the y prime direction. Nothing will happen. There is only a small change. That this is the output result. So we have already seen that Ex prime equal to E0 cos omega t minus delta minus E0. This is the index modulation part, and sin omega t. When we consider, instead of X prime polarized, Y polarized input light, you will get the equation. Same, the minus is changed to plus sign. That is the only difference. So you can choose any direction. The input light can be polarized either along X prime direction or Y prime direction. Anyway, you will get a modulated phase modulated output from the crystal. Okay, now here is the comparison. Longitudinal and transverse electro-optic modulator. Here you can see that the electric field is applied across the length of the medium. Here you can see the electric field or voltage is applied across the width of the medium, and here the transmission or propagation direction is along the Z direction. This is the propagation direction, that is Z, and input light is polarized along the X prime Y prime plane. Okay, these are the major things that you have to remember in longitudinal configuration. And in the transverse configuration, you can see Y prime is the propagation direction. Y prime is the propagation direction, and the electric field is applied along the Z direction. Z direction, and input light is polarized along this direction, that is X prime Z direction. Okay, so input light is polarized along X prime Z plane in the case of transverse modulator, and here in longitudinal modulator it is polarized along the X prime Y prime. This is very important to write the equations. Okay, so this is the main. Now, birefringence. I already told that in the longitudinal case, the refractive index is changing along X prime and Y prime direction because input light is polarized in the X prime Y prime direction. So the changes is these two cases. But in the case of transverse electro-optic modulator, we just told that the electric field is polarized along X prime Z direction. Okay, Z direction is actually the direction for extraordinary ray. So there is a change in the X prime direction, which is N0 plus half N0 cube R63 EZ. So the change in refractive index or induced birefringence in the case of longitudinal 0 cube R63 EZ, but in the case of transverse, take the difference between these two equations, you will get the induced birefringence, which is N0 minus Ne plus half N0 cube R63 EZ. So these are the induced birefringence in comparison of longitude and transverse electro-optic modulators. Now we have to see what is the net phase shift or retardation between the polarized waves along X prime and Y prime in the longitudinal case, and the induced retardation or phase shift between X prime and Z components of the in case of transverse modulator, transverse linear electro-optic modulator. Okay, now the induced or retardation can be find out as phi equal to delta phi X prime Y prime. That is delta X prime minus delta Y prime is the phase shift or retardation, which is equal to the phase difference can be estimated using the equation 2 pi by lambda into the change in the refractive index into the length of the medium. So delta n we know, just substitute the value here, you will get, and E equal to V by L. So L and L cancel each other. So the remaining phase difference is, or induced retardation or induced phase shift is 2 pi by lambda N0 cube R63V is for longitudinal electro-optic modulator. But in the case of transverse electro-optic modulator, the phi induced phase difference is delta phi X prime minus phi X prime minus phi Z, which is equal to 2 pi by lambda delta n X prime Z into L. So delta n X prime we already estimated in the previous slide. Just substitute that here. You will get this equation. Here you can see that there are two terms. One is constant term and the other depend on the voltage term, input applied voltage term. Okay. Now, the first term responding to the phase shift with zero applied voltage. So this will exist. Okay. If you will not give any voltage in the input. Okay. So the total phase shift is delta phi when V equal to 0 plus delta phi due to the application of electric field. Okay, so this is the comparison for longitudinal electro-optic modulators. Okay, now the half voltage comparison. In the case of longitudinal electro-optic modulator, we have already seen that the half voltage is lambda by N0 cube R63 1 by 2, and we have estimated value for KDP plus 8.3 kilowatt. Okay, but in the case of transverse electro-optic modulator, here is the equation for the delta phi. From the previous slide, you will get that this is the change. Okay, this is the change. So this is delta phi with V. When this is equal to pi, it will become a half wave plate. So pi equal to pi by lambda N0 cube this. And here V pi, the half voltage V pi can be written as lambda by N0 cube R63, which is similar to this term. And here one additional term is there, that is D by L. That means in transverse case, the half voltage is directly depending on the width of the crystal and inversely depending on the length of the crystal. Whereas in longitudinal case, it is independent of the nature of the or size of the crystal. Okay. Now, these are the features of longitudinal and transverse configuration. In longitudinal electro-optic modulator, we know that electrodes are placed in the opposite sides of the crystal, which may block or which may obstruct the incident beam. Okay, because electric voltage is applied across the length of the medium, so it may block the incident beam. Therefore, we have to use a ring type or transparent electrodes in longitudinal case. Whereas in transverse mode, electrodes do not obstruct the incident beam because it is applied across the width of the medium, which will not block the incident ray. Okay, so normal electrodes can be used in transverse case. Okay, now the applied electric field for longitudinal case is V by L because voltage is applied across the length. Here, the applied voltage, applied electric field is V by D, where D is the width of the crystal. Okay, now we have seen that half voltage is independent of the length and width of the medium in the case of longitudinal case, whereas in transverse case, the half voltage is directly dependent on the width and inversely depend on the length of the medium. Okay. Now, the longitudinal case is this, and the phase difference or induced retardation for transverse case is this. And here also, the induced phase difference for longitudinal case depends only on the applied voltage and is independent of the length or width of the medium. But here, the phase difference or induced retardation is directly proportional to the applied voltage, directly proportional to the length of the medium, and is inversely proportional to the width of the medium. So we can control the size of the medium and control the phase retardation in the case of transverse medium, but it is not possible in longitudinal case. Now, okay, phase modulation is over. Now we have to move on to the amplitude modulation, which is only for longitudinal configuration.
Sorry for the interruption, ma'am. Hello, ma'am.
Okay.
Actually, we have already exceeded more time from our actual time of the session, but we'll be extending the session for 15 more minutes, just to remind you about the time.
Okay. Okay, thank you. Okay, now we are over to the amplitude modulation. So the setup of amplitude modulation is this. We have inserted a crossed polarizer at the output. It was not there for phase modulation. Okay, this is the only change. So now the superposition of two retarded linearly polarized wave at the crystal output may lead to an elliptically polarized wave here. And this elliptically polarized wave is passing through the crossed polarizer. The polarization direction for the input polarizer, and this is perpendicular to each other. Passing axis is perpendicular to each other. So just pass the electrically polarized light to the crossed polarizer, you can modulate the amplitude. Okay. Now, here we are assuming that Y is the polarization direction, or we can take X as the polarization direction for the input wave. There is no problem. Now we are assuming that Y is the polarized axis. So, input polarizer passing direction ആണ് Y എന്ന് പറയുന്നത്. Therefore, analyzer pass axis എന്ന് പറയുന്നത് X ആയിരിക്കും, closed position ആയതുകൊണ്ട്. Now, the emerging beam from the analyzer can be written as, this is the resultant electric field equation, which is Ex prime cos pi by 4 minus Ey prime sin pi by 4. This is the equation. Now, we have already seen that this is the equation for the emergent wave at Z equal to L length. Now, same equation we are using here. Instead of cos, we are writing exponentially. Complex term we use it. So, Ex prime at Z equal to L is this, and Ey prime at Z equal to L is this equation. Okay, the same equation can be rewritten like this. There is no change. Only exponential term is written as e raised to. That's all. Okay. Now Ex prime and Ey prime you have. Now substitute these values in the resultant field equation. This one. So you will get this equation. Okay. So ഇവിടെ നമ്മൾ constant part omega t minus delta എന്നുള്ളത് പുറത്തേക്ക് എടുത്തേക്കുവാണ്. So remaining terms are here. Okay. Now gamma is, this term is gamma. This is gamma, K0 N0 cube. So we are writing it as gamma. Okay. Now, so this equation, and here in the input side, the amplitudes are along X prime and Y prime direction, and they are of equal magnitude. Okay. So retardation വരുന്നത് field in the presence ലാണ്. അപ്പോൾ in the absence of the field ആണ് input light വരുന്നത്. So other equal magnitude ആയിരിക്കും, that is A by root. Just substitute that here, you will get this equation. Now the e raised to I theta minus e raised to minus I theta എന്നുള്ളൊരു ഫോം ഇവിടെ കിടക്കുന്നുണ്ട്. ഇത് divided by 2i ഉണ്ടായിരുന്നെങ്കിൽ നമുക്ക് അതിനെ sin theta എന്ന് എഴുതാം. So 2 already is there. So ഒരു I കൊണ്ട് നമ്മൾ multiply ചെയ്തു, divide ചെയ്തിട്ടുണ്ട്. So this part will become sin gamma by 2, and this I along with the constant amplitude will become a complex amplitude. That's all. Okay, and this term is the delta prime, new phase change. Okay, so this is the equation for the electric field at the output of the analyzer. Now we can find the intensity at the output. So this intensity is half, since this is a complex factor, we can find out I equals to half of the real term in the E into E standard real intensity. That is 1 by 2 A square sin square gamma by 2 is the intensity factor. So the A square by 2, A by root 2 ആണ് നമ്മളുടെ amplitude at the input. So A square by 2 എന്നതാണ് intensity at the input. Okay, so original intensity. So that can be written as I0, and sin square, what is gamma? Gamma is actually this factor, which can also be written in terms of half voltage as pi V by V pi. So substitute that here, you will get this equation. This is the intensity equation. Okay. Now find out the transmission factor. The output intensity divided by input intensity. From this equation, you will get sin square pi V by 2 V pi. This is the output intensity in a transmission factor. This we have plotted here versus the applied voltage. So this is the amplitude modulated signal, and this transmission factor will be maximum when V will be equal to V pi. So this term will be 1. So I equal to full incident light will be transmitted when half voltage is applied. That is the importance of half voltage. Okay. Now we have to apply the modulation or amplitude modulation. So for that we have to vary the input voltage V equal to V0 cos omega t. So the transmission factor I equal to I by I0 equal to sine square. ഇക്വേഷനിൽ വിയുടെ സ്ഥാനത്ത് നമ്മൾ ഈ V0 cos omega t എന്നിട്ട് കൊടുത്തു. This is the equation. Now we are considering a weak signal with V0. The peak V0 is very much less than V pi. We are considering this. So ഒരു weak signal ആണ് നമ്മൾ ഇവിടെ consider ചെയ്യുന്നത്. In such case, V0 is very much less than V pi എന്ന് പറഞ്ഞാൽ this term will be very small. And using small angle theorem, sin theta is approximately equal to theta. We can write the RHS as theta square, that is pi by 2 V pi, V0 cos omega t whole square. That is the transmission factor for the weak signal. Okay, and which is equivalent to pi square V0 square by 4 V pi square into cos square omega t. And cos square omega t can also be written as 1 plus cos 2 theta divided by 2. Okay, so this is the final transmission factor, and from this you can see that the transmission factor or intensity is proportional to V0 square. It is not voltage. And also this is the input wave which is at frequency omega. This is the input wave and frequency omega ana, but we get an amplitude wave modulated signal at a frequency of 2 omega. This is a problem. So there are two problems here. One is there are three problems here. One is the modulated output is not linearly related to the input voltage. It is quadratically related. That is one problem, because we are dealing with linear electro-optic effect. So it is not possible to depend on the applied voltage. So this is one problem. And for weak signal at omega, we are getting the modulated signal at 2 omega frequency. That is another problem. And also look at the depth of modulation. So depth of modulation, V0 is very small signal, so depth of modulation is very small. Three problems are there. So we have to overcome this problem. This can be overcome only with the support of an external bias. So we have to use an external bias so that the transmission factor I by I0 should be half, even for zero signal. So this has to be done. Okay, so there are two methods for doing. One is apply a bias voltage of V pi by 2. അതായത് half voltage ന്റെ half എടുത്തിട്ട് നമ്മൾ ഒരു bias voltage കൊടുക്കുക. And the second method is optical biasing. But here, just think about the half voltage of KDP crystal. It was 8.3. We have already calculated. So 8.3 kilowatt. So we have to apply some 4.115 kilowatt for doing this external bias. That is not practically possible. So we have to select this second option, that is optical biasing, to make the transmission factor half for the zero signal. Okay, so we are considering optical biasing in order to overcome the three problems that we faced. Okay, now optical biasing setup is simple. Just introduce a quarter wave plate between the crystal and analyzer. Just before the analyzer, ഒരു quarter wave here. And also make sure that its fast and slow axis are parallel to X prime and Y prime axis of the crystal. Okay, of the polarized light. So fast axis X prime, slow axis Y prime light set cheyana nammal. So what this will do, this quarter plate introduces an extra phase shift of pi by 2 between Ex prime and Ey prime. Ex prime and Ey prime are the orthogonal components that components of electric field that is emerging from this crystal. Okay, so it introduces an extra phase shift of pi by 2 here. So it will give a modulated transmission of 50%, even for no signal, We will see that. Okay. So this is the old equation, electric field equation. Okay, just before biasing, this was the equation. Now we have this is the x and y prime term for the electric field. So due to the introduction of a quarter wave plate, an additional phase shift of e raised to I pi by 2 is coming here. Okay, so e raised to I pi by 2 is actually I, that is cos theta plus I sin theta. So I will come here and just take e raised to I gamma by 2 outside. So it will become this, and this equation will be this. Now find out the modified output. Now find out output intensity. This is the electric field. So you can find out output intensity as half of E into E star. This will give 1 by 4 A square 1 plus sine gamma. You can do that and see this is the equation. Okay. Now gamma is, what is gamma? Gamma is pi V by V pi. Just substitute that here. And A square by 4. What is A square by 2? That is I0. Okay. So 1 by 4 can be split into 1 by 2 into 1 by 2. So A square by 2 is I0 into 1 by 2 sine 1 plus sine this. Okay. This is the output intensity. Now find out the transmission factor I by I0, which is equal to 1 by 2 into 1 plus this. Now apply a sinusoidal voltage. Okay. This is the sinusoidal voltage, and assume a weak signal. That is V0 is very much less than V pi. A weak signal is applied. So this equation, weak signal equal to theta. So 1 plus pi V by V pi in the value. And V in the V0 cos omega t, sinusoidal voltage apply. Okay, this is the new transmission factor after biasing. Okay, now we can compare what was there before optical biasing and what was there after optical biasing. This is transmission factor before biasing. Now the transmission factor will become this. So from this equation, it is clear that before biasing, it was proportional to V0 square. Now it is proportional to V0. And earlier it was modulated at 2 omega frequency. But here, now after biasing, it is modulated with a frequency, same frequency. Okay. So, and this is the modulated signal. Earlier, before biasing, the modulation I by I0 transmission factor was very less, but now with optical biasing, transmission factor is increased minimum up to 1 by 2. Okay, so and output frequency is also changed to omega. Okay, so we have solved all the problems, and here the modulation depth, this is less that we have seen here, and here it is more. This is the modulation depth. So all the 3 problems solved with the help of optical biasing. Okay, that's all about our class. So in summary, we have learned we have just introduced the terms birefringence, retarders in the introduction part, and we have studied about modulation and types of modulation and different types of external modulators and electro-optic effect. 2 types of effects are there, linear effect and quadratic effect, and we have studied in detail and longitudinal and transverse modes of operation. And finally, we have seen the phase and amplitude modulation for longitudinal and transverse case. That's all about this portion. And here are the acknowledgements. And thank you.
Thank you so much, ma'am.
Okay.
It was a really descriptive session. I think even there is no space for the students to ask queries. Everything was well explained.
Okay.
Thank you. So, dear students, all your queries, if in case you have any queries, your queries will be addressed through our offline mode. So thank you so much. Thank you so much for your participation. Thank you, ma'am.
Okay, thank you very much.